Welcome back, class. We're attempting to refigure out uh, what goes in each of these boxes for this question of how many ways can I put m objects in n boxes subject to whatever conditions I want, whether the objects are distinguishable or indistinguishable or whatever. And so in this video, I wanted to remind us about this little p of nk, which is the number of partitions of n into k parts, and big S of nk, the Stirling numbers of the second kind, is the number of ways to distribute n distinguishable balls into k indistinguishable urns, so that no urn is empty. Okay, one of these is fairly nice, namely this one. That one is pretty literally put distinguishable objects in indistinguishable boxes so that no box is empty. So very literally, this is SMN, big S of MN. Okay. So that one's out of the way for now. Let's talk about what's happening with P of nk. So remember, when we talked about partitions, I know it's been a bit, we're talking about things like writing 10 is 4 plus 3 plus 3, or 12 is 6 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Okay, so P of 10 was counting all the different ways to do this, and P of 12 was counting all the different ways to do this. And that, again, that's little p of 10 and little p of 12 that I'm talking about there. But we also talked about things like little p of 10, 3 here, which is representing the number of ways to write down a partition of 10 into exactly 3 parts, that is with 2 plus signs if you want. So it's counting things like this, whereas this thing would be counted by p of 12, 7, because it's a partition of 12 into 7 parts. Okay. Remember, for all partitions, we don't care about the order in which these numbers are written. So we're just, by convention, always writing them in decreasing order because that makes it easier to list all of them. Okay. So it's then maybe surprising that something like P of 10, 3 would appear anywhere in our table of questions about putting balls into urns, because it doesn't seem to have anything to do with that by our definition of it. But here's what how I want to think about this. I want to think of, okay, so we've got 10 is 4 plus 3 plus 3. So we're always know when we're looking at P10, 3 that we're going to be looking at 3 total slots. And so I'm going to view this as being in some sort of correspondence with this distribution of dots into boxes. Okay. This 4 plus 3 plus 3 corresponds to saying I'm going to put 10 balls in 3 boxes, 4 in the first, 3 in the second, 3 in the third, except, again, the order doesn't matter, so really I'm just saying I'm putting 4 in one box, 3 in another box, and 3 in yet another box. Okay. And so you might realize after a bit of squinting at it that what I'm really doing here is I'm putting indistinguishable objects in indistinguishable boxes so that no box is empty, right? Because my partition is not allowed to have a plus 0. These all have to be positive integers. And so that means that we're actually talking about this square here. Namely, we're here talking about little p of mn. That's what this is counting. Now, if you have a very good memory, you might remember that when we did this in lecture, we did exactly this backwards. So we started with saying, okay, if I thought about putting indistinguishable objects in indistinguishable boxes, what would that look like? And we drew some pictures like this, and we eventually figured out, hey, this is doing a lot of work. Let's just write it like this. And that sort of unraveled us back into the question of partitions. Okay. So then, let's go ahead and figure out what happens if I don't insist that every box end up having something in it. So that is, if I change from talking about, as we were here, insisting every box have at least one object, to just no restriction. So I'm going to put distinguishable objects, m distinguishable objects, in n boxes, which I may or may not use all of. Okay. Well, then there's a question, well, how many boxes did I use? Well, if I used one box, well, then that's just S of M1. If I used two boxes, that's S of M2. If I use three boxes, that's S of M3. And so what this what this slot in the table is, it's actually a sum of the big S Stirling numbers. Namely, it's going to be the sum, as I goes from 1 to n, of S of M comma I. Okay. So each item in this sum is the number of ways to use exactly I of the m boxes. For very similar reasons, if I look at this slot, well, now I'm talking about indistinguishable, and so I should now be looking at the number of partitions instead of into exactly n parts, I should be looking at the number of partitions into up to n parts. So this cell in the table will end up being the sum as I goes from 1 to n of P of mi. Namely, that's the number of partitions into one part plus the number of partitions into two parts, etc. So again, using one box, using two boxes, using three boxes, and so on down the line. All right. So at this point, we're missing this box, which you might recall was a day of lecture that we'll briefly talk about again. We're missing these two boxes, which will turn out to be interesting things that I'll let you think about, but that might surprise you. And then we'll talk about these two. All right. Until next time, stay safe.